We're back with Chapter 7, the energy equation, and we're just going to have a very quick section here on the contrast of the energy equation with the Bernoulli equation. This is section 7.6. Should be fairly rapid to get through this. It's very important, but this is a pretty short section in the book. So let's just scroll forward, and here we are. We're looking at contrasting the Bernoulli equation and the energy equation. And the first thing that we want to point out is the energy equation is not the Bernoulli equation. And if we look at this we can look at the equations, we can see that there are several things that are different here, and I'm just going to highlight those in red. First of all, with the energy equation, we have the kinetic energy correction factors, which basically allow us to take a kind of an arbitrary velocity profile and express it in terms of the mean velocity, the area-weighted mean velocity. And so these two things are different. The other thing that's different about the energy equation than Bernoulli's is we are able to input energy in terms of what is called the pump head, which we've talked about before, and we're able to extract energy for our use through the use of turbines, and this is expressed in terms of the turbine head. We also have viscous losses in the systems in terms of the head loss, and so these are different equations. And if we think back, let me just state this. If we think back, this equation was really derived through the use of Newton's laws, and we applied them along a streamline. And so this was really a very different way than this, where we use the first law of thermodynamics. And so these were derived in two different ways, and they are really two different equations. And remember that this is dealing with energy, or the rate of energy, and we remember that we took the first law of thermodynamics and then expressed that as an open system through the use of the Reynolds transport theorem. So if we make a summary now of Bernoulli's equation, remember that we apply this, we select 2 points, and we apply this along a streamline in the flow. And the assumptions are that it's steady, incompressible, and inviscid flow. And the energy equation really is to select a control volume, actually, and to select an inlet and an outlet, which are control surfaces, and then equate the terms as they apply to the control volume between the inlet and outlet. And the assumptions are, again, steady and incompressible, but in this case we can allow for viscous flow, and we can, and that basically comes out through the head loss. And we have, as I showed before, these additional terms where we can add energy via pumps and extract energy via a turbine. So the final thing is to just state that the energy equation can actually be reduced to Bernoulli's under certain circumstances. If we have no head loss, if we have inviscid flow, then the head loss is 0. If we don't have pumps or turbines, then those terms cancel out. And if we have a small pipe, wherever we have, well, I should just say wherever we have alpha equals 1, and this is one case, then the equation will just reduce right back to Bernoulli's equation. And so if we just go back 1 second and see that if this is 0, these two things are 0, let me just cross them out. We cross these two out and set these things equal to 1, then we get the Bernoulli's equation. And so that's it for section 6. The main thing is to remember this fact right here. The energy equation is not the Bernoulli equation, and remember how to apply each. Okay, thanks.